Hi, welcome to the Calculus 3 problem practice sections here. So today, this video, we're going to take a look the the problems we're going to practice is related to the Stokes series here. So first, let's take a look at what is the Stokes series. So in here, this is related to the surface integration, also like we talked on the previous videos here. All right, so let's set a stroke series. So S be a smooth, simple, and connected or retainable surface bounded by a simple closed curves here. So this is the keyword we want to say is a closed curve C here. And then your field, that you can set a field, a vector field, F equal Pi, Qj, and Rk. And then PQR are the component functions. Then here, C is the positive orientation. So basically, this is telling you here, we know the curl of the F, right? So we know the curl of F. This is a vector field. Okay, this is a vector field. So basically, what do we have here? So take a look here. Okay, so basically, what do we have over here? The curl and the dot ds. So this is a surface integration with respect to a vector field. Curl F is a vector field. So then we said this ones here will be equal to the vector field F. And then you can integrate for the line integral. So what is the C here? C is a closed curve, and this surface S is bounded by this closed curve. So when we look at this formula here, this is what we call this Stokes formula here. All right. So the problem we're going to practice for this section is the first is so why this is helpful. So first things here, we can start from here. That's what we're going to practice in this video. So sometimes you want to do the surface integration for here. Then it turns out to be pretty difficult and tedious to do, then maybe you can try the line integral. Then the second type of the problems here is when you try to do the line integrals and sometimes become tedious and very complex, very complicated to do it, then maybe you can try to use the surface integration concept to do that. All right. So remember in the previous video, we talk about the surface integrations, right? If you can find the parametric equations, or your z can be right a function of g of x, y, then we can apply the surface integration formula to do it. All right, so now let's take a look here. Let's go back to our problems here. So the first problems here, you said, use the Stokes theory to evaluate the curve f dot ds. Okay, so so in here, let's take a look why we want to do that. So you said, okay, so this is my f of x, y, z, right? So let's take a look at the curl. Okay, so let's take a look at the curl. The curls F, remember, let's use this opportunity, try to review one more time. How do I do the curl? We put the ij case, right? Okay, and then here we do this is the row x, row y, and the row z's, right? That's the operator. Then we put here is my function is x squared sine z. Then this is y squared, and this is xy. Then, like I said, this is a typical my way to do the determine. I move the first two columns out, so this is row x, x squared sine z, and row y, y squared. So now I can do the cross. So it's ding, ding, ding. Then minus the 1, I go the opposite, right? So I minus this one, this one's here. Okay, so let's try to do it. So here the I, all right, so the I is row Y, so I have xi, all right, xi, then j is row z, so then I have x squared cosine z, because then this is my j vector, then k is row x, row y, so this will be 0k, all right, then the green one minus, all right, minus k, this is x squared z, the row y, so I have a 0k here. All right, now I here is rho z and it's y squared, so I have 0i. Okay, then j is rho x, rho y, so I have what? Y j's here. All right, so now I combined here, I have xi, then the j's here, I have x squared cosine z plus y, the j, right? And the plus 0 case here. So the curl, I can write it as a function is x squared cosine z plus y and the zeros, right? So that is my curl. So this one is my curl f here. Okay, now I can always, so because I want to find the curl F, the ds, right? So the ds is here. Now remember we did it in the surface integration. We can just use the surface integration and try to do it. Let's see how. So the z, this one I can say this is my gxy here. Correct? All right, so then the gxy, because this is the above the xy planes here, right? But so I know the z, the z is greater than equal to zeros, right? So then I will have y minus x squared minus y squared, all right, greater than equal to 0. So I can have x squared plus y squared greater than equal to 1. So when z equal to, so when the z equal to 0, and then my curve is x squared plus 1 equal to 1 here. All right, so all this information is here, right? So if I want to use the surface integration, we can do that. So remember the surface integration is here. So if you just do this ones here, you say curl, then okay, so here. The ds, we say in here, you can do like what we have here. So remember, so it's a negative p rho g rho x, negative p, so it's a negative x, right? So we use the surface integration rho g rho x, right? So the rho g rho x will be the negative 2x here. So remember, this is the formula we used before. So here, this is the negative p and the times rho g rho x here, right? And then we will have a negative q. So it's a negative x squared cosine z plus y. That's right. So we have a negative cosine z plus y. And then times what? And then we will have here is times the negative 2y here, right? And then plus z is just 1 minus x squared minus y squared. Correct? All right, so this will be, so that's what will be our so the use the formulas here. So this will be what we have is here, then the dx dy here, right? So that's what will be our dx dy. So when you see here, so I'm integrating along the surfaces here, right? So here, take a look, this is negative q, This is rho g, rho y, like the formula we use, and this is plus what? This is plus r functions, right? So this is plus my r functions here. So my r functions, okay, I'm sorry, here the r function here will be zeros here, right? Because the r functions here will be 0. Okay, and then dx dy. So as we simplify that, okay, so the dx dy, now I have a regions here. Okay, so here is my regions here. All right, I think I should use the d. Okay, maybe I use the d better. Okay, so then you simplify here, you will get a negative positive 2x squared. All right, and plus the 2y squared, and then plus this minus, so plus the 2yx squared cosine z. Now I have a dx dy. So the dx dy, it's satisfied the x plus square. So it's z equal to the 1 minus x squared. So as you can see, if I do, of course, you can get this answer by integrate those, then plug into whatever, because I know the x squared plus y squared, right, equal to 1. So in here, it's pretty difficult to try to change it to the polar systems, right? So we know this one is hard to integrate. All right, so so we know this one's here is hard to integrate here. Okay, so that is why we say, okay, so if I want to use the curl, this is pretty hard to integrate. So then let's take a look. Can I simplify these problems here, right? So it's hard to integrate, and I don't even know we'll be able to integrate that efficiently, right? So it's hard to integrate. So that's why I say, okay, let's get help from using the Stokes theory. Let's see, can I do a line integrations here? And this is the f of drs here, right? So like I said, in here, physically, if you want to use the surface integration, it's very difficult to integrate. So let's take a look. To see if I be able to use the line integral. Okay, so line integral, as we say here, when the z equal to 0, this surface was enclosed by this circle at xy planes here. So I know so this is my surface here. All right, so this is my surface here. So I know enclosed by the xy, when in the xy, it was enclosed by this is my c's, right? So this is x squared plus y squared equal to 1. So this is what? This is the circles here, right? So what I can do here now is say, okay, I can use f dot drs here. So first, because I recognize my c's here is this enclosed circles here. Now I know circle is quite easy to find the parametric equations here. So I can define the RT equal to what? I can define that RT will be equal to the cosine t plus sine t. So we know the circle is easy to define. So I can say the RT equal to the cosine t and the sine t. And now my t is from 0 to where? 0 to 2 pi here, right? And then my R prime here, all right? So my R prime will be negative sine t I plus cosine t j here. Okay, and then in here, remember, so we said this integrations f here dot dr. So what do? We replace everything from the t. So right now I have a t from the 0 to 2 pi. Then I need to replace my field with RT here, right? Then these numbers here, I'm going to dot product R prime T. All right, so R prime T, if I put it into vector form, this will be the sine T, cosine T, okay? So now let's take a look here. Okay, so so let me get more space here, right? All right, so my F here, right? So now let's put it in the F here, right? So the F here is okay, so my F function, my F vectors here, if you remember here, okay, so here, the F here, if you go up, it will be x squared sine z, y squared j, x, y, k, right? All right, so here, my F I replaced with the RTs here. Okay, so now let's see here, just like we did the line integrals here. So we say F the RT. All right, so the f of the RT, so it will be x equal to the cosine t, right? So then the x equal to the cosine t. So I have a cosine square t times the sine z here, right? So I have a cosine sine t times FRT, the sine, okay? So the sine z, all right? And then I can do, all right, so in here, be careful, the sine z's, right? Here, the z, we know the z here is equal to 0. That's why I have these closed curves, right? So in here, be careful. So sine z, so what is the sine z will be? This will be sine 0 here. All right. Then the next component is y square j. So the y square, so this is the I, right? Plus y square. So y square will be what? So this is y, right? So we know this is xt, this is yt, right? Okay, so y square, so what are we going to be? The y square will be the sine t, the square j, then plus the k, xyk. Okay, xyk, so x is cosine t times xy sine t, right? So xy sine t, then this is my k components here. I substitute RT. Now in here, I can put it into a vector form because the sine 0 is zeros, right? So I have 0 sine t the square. Then this is a cosine t. So this is a cosine t sine t. All right. So I put into a vector form. And then now let's do FRTs, right? So this one is FRT dot product R prime T. All right, so here dot product R prime T's here. All right, so the dot product R prime T's here. So let's do it. All right, so let's see here. So this is 0 sine t square cosine t sine t. Then my r primes here is over here, right? So I dot the product negative sine t cosine t, right? Because this is I and the j's here, right? So this is I and the j's here, all right? So this is I and the j's. here, right? So this is I and j. So my k terms is 0, right? So this is 0. So when you do the dot product, what do we end up with? We end up with sine t square cosine t, right? Okay, so now we can put it into my integrations here. So now this one's here will be the C, the FDR. Okay, so it will be equal to the 0 to the 2 pi. Then this one I plug in will be the sine t square cosine t dt here. Did you see how easy this integration turns out to be? So in here I can use a simple u sub. I can just say u equal to the sine t and the du equal to the cosine t. So then this u sub will just give me the final answer is sine t to the cube to the 3, right? 1/3. Then I put in the 2 pi over 0. And then here is what is here? Is zeros here. So as you can see, compared to, try to this integration, the curl over the surface, right? It's very, this is very complicated for doing the surface integration. But now if you use the line integral, then this one, so because we know by the Stokes, I know this one will be equal to the curl F. Then if you do the surface integrations here. All right, so that is what is the first, the main things here. We talk about the Stokes theory, and it's very important, right? So you can, if they give you these functions here, so this example we did is if they give you, they want to integrate a surface integration, and for a given vector function, if this is a curl of that vector field, then you can use just the line integral over that field. Okay, so the whole purpose here is to simplify it, right? So it's simplified your integration. Otherwise, you still can use, just like we talked about before, you can use the surface integration. But now after you put it in here into the surface integration, then you will say, whoa, this part, this part is not easy integration. I think this one maybe still is workable by doing some integrated by part. You probably still workable, but it's just very difficult integration. So if you change it to the curve, then doing the line integrals here, so it will be pretty easy here. So like if you take a look at the other two problems, like this is arctan, x squared yz squared, and this is x squared y, x squared z squared. So just curl itself will become a very, these very difficult functions, right? So if you want to integrate, so how do I use how do I use the line integral to do that? Okay, so that is the whole purpose for the first part of the Stokes functions here. All right, so now for the part B, for the other problems here, like we see this is a very complicated function. So now let's just directly use the Stokes instead of like I said, we can always find the curl and then do the surface integration. So let's take a look at how do we do these ones here, right? So the first S is the surface, is the cone, right? From x equal to y squared plus z squared, x is from 0 to 4. 0 to 2 here, right? So now for this the things here, we know the boundaries here, okay? The boundary curve C is a circle. Okay, so this circle, if you square both sides, so this will be y squared plus z squared equal to 4, right? Because this is x squared equal to y squared plus z squared, but x from the 0 to 2, right? So then this is the closed by this boundary. This is the circles also. Okay, so now because we know this is a circle, now I know, let's try to do here the C, the FDRs, okay? So let's try to do one more time. Because it's a circle, we know very easy to define the parametric equation. So the RT, so it should be, because x equal to 2, right? So x equal to 2 is a closed circle. So it will be 2i, then the y, we can say is 2 cosine t. This is j, because here, this is y and the z's here, right? Y and the z's here. So then plus 2 sine t to the k, right? So this will be my r. Then I can find the r prime. All right, so the r prime will be 0i and minus 2 sine tj, then plus 2 cosine tk here. Okay, be careful. The reason why I use this is a 2, because this is circles, right, with radius equal to 2 here. Okay, so let me write this into the vector form. So this is negative 2 sine t, and this is 2 cosine t here. All right, so now let's try to put into the, okay, so now let me try to put it into the FRTs here, right? FRTs here. All right, so the FRTs here, so the, okay, so here is the FRT. Let's put here, this will be arctan, right? Because here this is arctan, x squared yz squared, all right? So x squared yz squared, x is 2, so 2 to the square, okay? So this is 2 to the square is 4 times y is 2 cosine theta. So that will be 2 to the square is 4, the 8, then times another 2, so it will be 32, okay, cosine t, right? 32 cosine t, z squared, right? So it's a sine t squared. Okay, so here, be very careful here. That's what we got here. This is, so this is your y, this is your z's, right? This is your x. So you just plug it into here. Okay, then this is my I. So let me put it into the vector form. Maybe it would be easier. So this is, right? And then my j, x squared y. X squared y will be x squared, so y, so it will be a cosine t, correct? And then x squared, z squared, so it's 4 times 4, so it's 16. So it's 16 sine t squared, right? Okay, so now I'm going to dot product r prime t. So it's 0, negative 2 sine t, and 2 cosine t. All right, so here let me rewrite this. So this will just be the FRT dot product r prime t. So you see here, so when you do a dot product, this complicated term disappear, right? Because the dot product was 0. Okay, so this will be negative 16 cosine t sine t, all right, then plus 32 sine t square cosine t. Correct. So then this will be my j. No, this is the right. So this is the dot product here. Okay. So after dot product, so then I know these things here will be equal to, right? So this will be equal to the negative 16 cosine t sine t, then plus 32 sine square t cosine t dt. So where is my t? Because this is a circle from the 0 to 2 pi. So for this ones here, it turns out this will be a pretty easy integration also. So this is a cosine sine, this is a sine square cosine. You can use a simple u sub and find the answers here, right? So I will just leave to you guys to finish this simple integrations here. All right, that's it for this video. So the next video, we're going to go backward. So in fact, find the line integral is way more complicated than find the surface integration. So let's see how do we do that. Okay, so now, let's stop it here so the video doesn't go too long. Okay, so talk to you later, and the last will be this videos here. Okay, bye.